Giusto.
Hi, first. Okay. Hello, everybody. First of all, thanks to the organizer for letting me speak at this conference. This means a lot to me since I was a student here at the University of Pisa. And without further ado, let me start with this presentation where I hope I will give you some new insights of the problem of solar radiation pressure semi-secular resonances. So I'm going to start with the full model and then go to refine it to develop toy models to focus on this particular aspect. We start with the perturbed vocabulary problem perturbed by the geopotential, unisolar perturbation, and solar radiation pressure. The Hamiltonian solar radiation pressure is actually based on the one using the cannonball approximation, which might appear pretty weird, especially in the case of a debris. But in the case of a satellite with a solar sail, cannonball approximation might actually be good because it can direct light to be always perpendicular to the surface. Notice the presence of the parameter area to mass ratio, which depends linearly on formulation. And let us have some assumption. For example, we're going to reduce our research to the upper Lie and lower Mie regions surrounding the Earth, considering only moderate to high values of the area to mass ratio, let's say between 1 and 40 meters square over kilogram. Using this, we can, as we can see from this picture on the right, say that the solar radiation pressure effect is dominant even with respect to the solar perturbation. So we have that J2 is the main perturbation to the Kepler problem, and we can consider as the secondary perturbation, the one to solar radiation pressure. We are going to consider a single average model because we're not really interested in short periodic perturbations. So a possible model of Hamiltonian is the one which includes only the value of the secular effect of the J2 and the 6 most relevant terms in the Hamiltonian expansion of the solar radiation pressure potential. This is due to in this paper satellite orbits perturbed by direct solar radiation pressure. We can see here some details on the form of the solar radiation pressure there. You can see that it depends on the semi-major axis and on basically on the eccentricity. And here we have the inclination functions of both the sun and the satellite. We see that we have as an argument the combination of angles which include the mean anomaly of the sun, and resonances involved with such fast angles are often called semi-secular. In particular, we wish to study a toy model which focuses on the effect of a single resonant term. For example, we mark it as HJK, depending on the resonant angle. Such models are non-autonomous, so we introduce a dummy action lambda s to make and we substitute with this Hamiltonian, making the problem now autonomous. Here, NS is actually the mean motion of the sun. Sorry, I forgot an equal here. And in the following, we're going to use the following notation. We're going to use the variable eta, which is equal to 1 minus g squared, but you can see it also as g over ma squared, where G and H are the usual Delaunay elements. Actually, due to a framework by Reiter in this extremely nice paper about unisolar axial resonances. So the idea is to proceed similarly to what he did. We rewrite the Hamiltonian in this form. We have this term na square, which is multiplying the formulas for the effect of the J2 and of the perturbation due to solar radiation pressure. And in order to reduce this 3 degree of freedom model to a simple one, we're going to use a simple canonical transformation, depending on each specific toy model under consideration. This canonical transformation is actually not gauge-free, so when we are going to convert the non-Hamiltonian, we need to divide by the valence of the canonical transformation, which is conveniently n squared, which was highlighted before. And we have this final point model, let's say. So we have this term depending on the motion of the sun, the term which includes the secular effect of the J2 and the term due to solar radiation pressure. To find the resonant equilibrium, we can then use simply the canonical equation of motion of Hamilton. We have, from the first equation, we obtained that the resonant angle would be equal to 0 or pi, and substituting in the second one, we obtain this equation in red, which we actually wish to approximate by dropping the term depending on solar radiation pressure. By the way, here the prime corresponds to the derivative with respect to the variable we introduced before. And we ask when, for which values of A and their mass ratio, this is a good approximation. To do so, we introduce the smallness parameter, epsilon. And we say that epsilon is not small when elements are getting close to 0.1. This is a dimensional number. And on the right, we can see some kind of validity region where this approximation holds. So it corresponds to the region where epsilon is smaller than 0.1. And we can see that in the region of interest, for example, even up to 20,000 kilometers of single major axis, we can consider pretty high values of the mass ratio ranging from 0 to even 1 or 2 meters squared per kilogram. With this approximation, we can then simply solve this equation to obtain some resonant curve, which describes the position in the eta alpha plane of the resonant equilibrium. Alpha is an integral of motion, and so by fixing a value of this integral of motion and considering the intersection with these resonant curves, we are going to obtain the location of the resonant equilibrium. Everything is described using this auxiliary variable ZP to make it a little bit more pleasant to the eye. And by simply plotting resonant curves for different values of these numbers ZP, we can appreciate how the location of the equilibrium qualitatively changes with variation basically on the semi-major axis. So going from left to right, the semi-major axis is increasing. The blue and orange curves correspond to regions where this approximation is actually not valid, because, for example, the blue curve corresponds to secular resonances, the one which does not depend on, which depends only on the inclination, so not on the eccentricity, while the orange curve separates branches of the curves into regions with equilibrium points with opposite indices of stability. These curves can be replotted in the inclination eccentricity plane to obtain a better insight and easier to understand in terms of the usual orbital elements. And as we can see, with the increase of the semi-major axis, this resonance curve recedes to region where the eccentricity is bigger. This is the case, for example, of another resonant term, the one with the index k equal to 1, and we can see that in this situation, this resonant curve might meet at a certain point, in this case, at alpha on the line alpha equal to 0. On the bottom, you can see the same plots in the inclination eccentricity plane. And now we're ready to provide some remarks. First of all, we noticed that the phase space resembles the one of a pendulum in the case far from eta equal 1 or t equal to 0. The stability can be easily assessed by studying the linearized variational equation far from the extremal points, or far from, let's say, the orange curve from what I showed before. And using the same approach by writer is really easy to obtain formulas which are really unpleasant to see, so I don't introduce here. But we notice that the amplitude of the resonant islands is proportional to the square root of the error-to-mass ratio. And this is pretty interesting. As we can see from these FLI maps, we can see that actually these right curves correspond to the intersection of the separatrix with the sigma equal pi or 180 degrees line. And at the increase of the error-to-mass ratio, we see that we have these curves, which actually called the one of the square root of the error-to-mass ratio. And we remark that the equations for the equilibrium exhibit a singularity at eta equal 1, and this is going to be really interesting in following. But first, using the formulas for an amplitude by Greiter, it's easy to obtain some insight of which resonance is the strongest. And as we can see here, I provided the maximum variation both in the eta variable marked with delta, but also with some insight on the variation of the perigee. And as we can see, the 1 minus 1 resonance, so the one corresponding to, just let me write it down, omega plus omega minus this resonant angle is the most important one. We can see that if we have an error-to-mass ratio equal to 10 meters square per kilogram, the variation in perigee might be as big as 4,000 kilometers, which is pretty remarkable in my opinion. And the second biggest is the one. The second biggest is the minus 1, 1, so basically this resonant angle. Well, for a value of the error-to-mass ratio equal to 10 meters square per kilogram, we obtain a variation in perigee of up to almost 3,500 kilometers. Fast definite indicators let us draw phase space in a pretty nice way, but they highlight a peculiar feature of this kind of resonances. In particular, if we consider two pendulum-like equilibria which are close by, and we increase the error-to-mass ratio, we see that the two islands start to merge. In this situation, we have almost a subtle connection, where we have that the unstable equilibrium point are almost connected by the separatrix, and increasing the value of the error-to-mass ratio, we obtain a phase portrait which is basically different from the one of the pendulum. It's also interesting to see that in these plots, the maximum value of the admissible eccentricity without collision is 0.3. So this kind of resonance seems to be not important because their center is in principle outside of the region of the admissible region. But increasing the error-to-mass ratio, this the resonant island could leak into the admissible region for the eccentricity. So even these resonances, especially at higher value of the semi-major axis, are usually for highly eccentric orbits. They could be relevant also for the smaller eccentricity cases. Fast leveling indicators are really a useful tool, as you can see from this plot. They let us draw some kind of bifurcation plots. Here, the bright curves correspond to either the stable point or the intersection of the separatrix with the selected lines, such as resonant angle equal to 0 or resonant angle equal to 180 degrees. But let me remark that in this case, we have this pretty weird behavior, this brighter curve, which is actually not a separatrix, but it highlights a problem of an issue with this model, which is often singular for value of eccentricity equal to 0. And indeed, if we study the behavior close to eccentricity equal to 0, we see that we have this kind of line with the color of a square matrix, but which actually correspond to the level set associated to eccentricity equal to 0. They stem from the angle sigma equal to 90 degrees plus or minus 90 degrees. And if we adopt quantitative variables and we replot these graphs, we obtain this, which are spaces reminiscent to the one associated to the extended fundamental model of resonances. In this case, it's actually more similar to the second, but it's more or less the same thing. And we can see that with the increase of the area to mass ratio, we tend to lose equilibrium. So we have, at the increase of the area to mass ratio, we have less and less equilibrium point. For example, in this last situation, we just have 1. At even moderate value of the eccentricity, because it's almost 0.1. So let me remark the conclusion of Amplitude work of this presentation. We provided the approximate for the location, stability, and amplitude of the presented problem. We described the interesting phenomenon of the merging of nearby resonant islands and allied connections with the extended fundamental model. Future works include a formal modeling of solar radiation pressure effect in the context of the extended fundamental model, and the inclusion of the unisolar perturbation to have a more realistic model. This could be done as well in the context of the extended fundamental model and to have some kind of mixed model of resonances. Thank you for your attention, and I'm not